In this video, we'll talk through the notes for section 1.9, which is called Classification of PDEs. So far, we have encountered three significant second-order partial differential equations that are important in the study of physics and other subjects. The first one is the heat equation, or more generally, the diffusion equation, which is u sub t minus some constant times the second partial of u with respect to x is equal to 0. That is to say, the first derivative with respect to time is proportional to the second derivative with respect to x. This is called the diffusion equation because it can be used to model any kind of diffusion or spreading, or at least many kinds. The second significant second-order partial differential equation that we saw is the wave equation, which tells us that the second derivative with respect to time is proportional to the second derivative with respect to x, or the spatial variable. This equation is very useful when you're looking at something which propagates or transports. The third second-order differential equation that we saw was Laplace's equation. And this is a relationship that doesn't involve time. This is about the spatial variables. In 2 dimensions, it's the second partial with respect to x plus the second partial with respect to y equals 0. In 3 dimensions, we have plus the second partial with respect to z in there as well. 1 and 2 are called evolution equations because they describe a process that evolves over time, because there should be a y there. So they're called evolution equations. They describe a process that evolves over time. Number 3 is an equilibrium or steady state solution that doesn't depend on time, just on the spatial variables. In terms of physical processes, equations like the heat equation are called diffusive because they describe a process where something is spreading out, and equations like the wave equation that describes a process where something is being propagated or transported, those are called wave-like. Equations that do not describe a process evolving over time are known as static. Let's consider the general linear second-order partial differential equation. Notice that this is linear, and again, by linear we mean it's linear in terms of u and its derivatives. This is second order, so that means we have the second order derivatives, u sub xx, u sub xt, and u sub tt. Here we have a bunch of coefficients, a, b, c, e, and f, and g. We don't include d because we're going to need d for something else in a minute. But really we're interested in the part involving these second-order derivatives. That's known as the principal part. And that's the part that will determine the classification of these partial differential equations. We just remark here that there's this f term. Now, if that f term, this lowercase f I should say, since we have an uppercase f here too, this lowercase f term, if this function is 0 constantly for all x and t, then the partial differential equation is called homogeneous. Otherwise, it's called inhomogeneous. Now, the way I've written it here, it looks like all of these coefficients are constant. And indeed, for our examples and our study, that will generally be the case. But it's okay if these coefficients are not constants. It just makes the study a lot more complicated. So, if the problem only depends on spatial variables, as in Laplace's equation, then we'll replace xt with xy, and then we'll still have this general linear second-order form, but we'll just replace t with y. So the classification of second-order PDEs depends on the principal part. So that's why I've left that on the screen, even though I've scrolled up. We define something called the discriminant of the PDE, and it's the number d, capital D, this is why we didn't use capital D earlier, is equal to capital B squared minus 4 times capital A times capital C. This should look familiar. When you're studying quadratic equations, there is something called a discriminant that usually is written in a similar way, and it determines the nature of the solutions. And in a similar way, this discriminant determines the nature of the PDE. If d is greater than 0, the PDE is called hyperbolic. If d is less than 0, the PDE is called elliptic. And if d is equal to 0, the PDE is called parabolic. So these names also come from the study of curves in two-dimensional space, and it's no coincidence that they're called these things. So we've seen examples of second-order partial differential equations, and let's classify them. The heat equation is parabolic. If we write the heat equation in what you might want to call standard form, at least let me scroll back, at least in this form here, if you write the heat equation in that form, then it looks like what you see here. U sub t minus, oh no, it's not done yet. Here, we have it right here. Minus k times u sub xx plus u sub t equals 0. So this isn't the way we've usually been writing it, but if you write it in this way, then you can easily see that a is equal, and this is capital A of course, is equal to minus, capital A is equal to minus little k. B and c are both equal to 0. So that means the discriminant, since b is equal to 0, and c is equal to 0, the discriminant is equal to 0. So that means it's parabolic. The wave equation is hyperbolic. This one is also not usually written in what we might call the standard form, but we can easily rewrite it that way just by swapping the order. So here we see that a is equal to minus c squared. Now this c is a lowercase c. It's kind of hard to tell when I've just written them out like this. But this is a lowercase c. And this is an uppercase C. Like so. So now we can compute the discriminant, and it's capital B squared minus 4 times capital A times capital C. In this case, B is equal to 0. A is equal to minus lowercase c squared, and capital C, uppercase C, is equal to 1. So you end up with 0 minus 4 times a negative c squared times 1 is 4c squared. Since c is assumed, well, c is assumed to be a real number, c squared is positive, so 4c squared is also positive. So that means the discriminant is positive, and therefore the equation is hyperbolic. Laplace's equation is elliptic. In this case, we don't have to rewrite it. We see that capital A is 1, capital B is 0, and capital C is 1. So the discriminant, you can see, is equal to minus 4, which is negative. And so Laplace's equation is elliptic. Let's move to the next page. Our objective now is to find a change of variables, or a change of coordinates, really, that allows us to simplify the principal part. The principal part is the only part that we'll be looking at. We're not going to really consider the lower order derivatives until we actually look at an example, and then they become important. But for the classification, it's only the principal part that we need. We're going to find a change of coordinates. These new coordinates will be called xi and tau, and they will be obtained from the original coordinates. So we want to construct a linear transformation here. So we have xi is equal to ax plus bt, and tau is equal to cx plus dt. Since it's a linear transformation, we can write it as a matrix equation. And I did that here because I want to make sure that we understand this assumption that we want to make, that AD minus BC is not equal to 0. That's the determinant of this matrix. So we want to make sure that that determinant is non-zero because we want this transformation to be invertible. That is to say, we want to be able to go from xt into xi tau and vice versa, the other way around. And we can only do that if the transformation is invertible. Now, I'm not entirely sure that I should have used the word assume here. We're choosing this transformation. We're choosing these new coordinates. So really what I want to say is we want to make sure that AD minus BC is not equal to 0. Now, I should be a little bit careful. I'm talking about lowercase ad minus bc here. So now we have lowercase a, d, b, and c, or a, b, c, and d, I should say. And we also have uppercase a, b, c, and d. Those are here. Well, you don't see the d, but the d is the discriminant. So we have lowercase letters and uppercase letters, but we'll try to make it clear which ones we're talking about. So the state function in these new coordinates, c tau, will be denoted by capital U. We did this before in a previous section. So we start with U in the coordinates xt, and we transform the state into a new function. It's really the same function, it's just expressed in terms of the new coordinates. Now there is a relationship, of course, and it's that so lowercase u at xt is equal to uppercase U at ax plus bt, comma, cx plus dt. Okay, now if we know this relationship, we can compute the derivatives of lowercase u in terms of capital U. We want to do this because our objective is to look at this principal part of the equation, and we're hoping to simplify it in some sense. And by simplify it, what I really mean is I want to get rid of some of these terms in the new coordinates. So in order to do that, I want to determine what these partial derivatives, what these second-order partial derivatives of little u are in terms of capital U. And we can just do that using the chain rule. So here we've done that for partial u, lowercase u, with respect to x. And that's uppercase U with respect to c times the derivative of c with respect to x plus the derivative of capital U with respect to tau times the derivative of tau with respect to x. And since c and tau are linear, we just end up with constants here. Linear in terms of x and t. So the derivative of c with respect to x is a, and the derivative of c with respect to t is, the derivative of tau, so the derivative of c with respect to x is a. We're doing the derivative of this one with respect to x. And then we're going to do the derivative of this one with respect to x, and that's c. So that's where this c comes from. Similarly, we can find the partial derivative of u with respect to t, lowercase u. And it's the same sort of computation, just switching variables. So this gives us our first order partial derivatives, and now we want the second order partial derivatives. So we look at the derivative of u, lowercase u, with respect to x twice. So that's the derivative with respect to x of u sub x, lowercase u sub x. And we know what that is. We've just computed it. It's right here. So that's the same as this one. So there are two terms here, and we're going to have to use the chain rule for both of them. So we've re-expressed that as the derivative of the first one. Let me just change the color here. The derivative of the first one times that constant a, plus the derivative of the second one here times that constant c, because you can take the constants out. Okay, so now we want to compute the partial derivative of capital U sub c with respect to x, and we have to use the chain rule. So we differentiate capital U sub c with respect to c, then multiply the derivative of c with respect to x, which is this thing right here, and then we add in the derivative of capital U with respect to the derivative of, remember what we're differentiating here is this u sub c. Let me just change the color here. We're differentiating this thing right here, that thing. We're differentiating that thing. So first you differentiate it with respect to c, which is this one right here, and then you differentiate with respect to tau, which is right here. But of course you have to use the chain rule. So you differentiate u sub c with respect to c, and then multiply that by the derivative of c with respect to x. And then we add to that the derivative of u sub c with respect to tau, which is this one. And then you multiply the derivative of tau by the derivative of tau with respect to x, which is that. And again, the derivative of c with respect to x is just our constant a, and the derivative of tau with respect to x is c, just like it was before. Okay, so that's the first one, the first term. But now we want to differentiate u sub tau. So first we differentiate it with respect to xc, and then multiply by the derivative of xc with respect to x, which is a, like it was before. And then we add in the derivative of u sub t with respect to, or u sub tau with respect to tau, and we multiply that by the derivative of tau with respect to x, which again is c. So notice we have a bunch of a's and c's, so we can simplify this. So we have u sub c times a times an additional a, so that's going to give us that a squared right there. And then we have u sub c tau times c times a, so we're going to have that right there. So the blue terms give us those. Notice that there's a 2 here. That's because we're going to get one of these from the other term as well. So here we have a mixed partial times a times c, which is exactly the same as what we had before. So that's this one right here. And then we have this term, which is the second derivative with respect to tau times c times c times c times c. That gives us that c squared. So from the second term we get that. So there's some overlap there. So in the next line I just rewrote it, so I put all of the constants first here in front. Okay. Now that's an elementary computation which is not trivial. There's a lot of room for error, so I'm not going to go through the remaining partial derivatives in detail, but I have computed them here. So you can see that the second order derivatives, we've computed u sub xx, then we have a u sub tt, and a u sub xt, the mixed partial. These are all the, let's see if I can find yet another color here. These are all of the second order terms, the second order partial derivatives of lowercase u. So what we're going to do is we're going to go back to our principal part here, and we're going to just substitute in u sub xx, u sub xt, and u sub tt in that equation using these formulas. Let me just underline them like this. Okay, so we've computed those. So here we have the principal part, which is capital A times lowercase u sub xx plus capital B times lowercase u sub xt plus capital C times lowercase u sub tt, like that. And then we just substitute them in. So we've got them up here. So u sub xx is this one right here. So that one goes right here. So again, maybe I should be color coordinating these a little bit. So I'm going to have to reuse colors though. So that uxx goes right there. And then uxt goes right here. And then u sub tt goes right there. So that gives us our principal part. And then we just simplified it. So how does that work? So we have so we're going to look at these u sub xc terms, and so we can just add them together, just adding along here. So we're going to end up with these terms right here. So let's see, so we have this term here, and then this u sub c tau, that goes right here, and then we're going to have this u sub tau tau term that's right here. So we're just adding together all of the u sub c terms, those go here, and then we're going to add together all of the mixed partials, which are right here, and those all go right here, and then the u sub tau tau terms, those are all right there. So let me just color coordinate them. So we have, so the green ones are the terms with the B's, capital B, so that's these. And then the orange terms are the ones that are with capital C, which are right here, like that. Okay, there we go. All right, so we've rewritten our principal part in this way. So it might not look like we've done much. In fact, we're trying to simplify it. It might look like we've made it more complicated. However, the fact of the matter is that we have a lot of freedom in how we choose A, B, C, and D, the lowercase a, b, c, and d. The uppercase A, B, and C are given to us, but we have a lot of choice over the lowercase variables, or the lowercase letters. We just have to make sure that AD minus BC is not equal to 0. So what we're going to do is we're going to choose values for A, B, C, and D that make some of these partial derivatives disappear. So our choices will depend on the discriminant, in particular whether it's positive, negative, or 0. The actual value is not the key point, but whether it's positive or negative or 0. So let's look at each case separately. So I'm going to leave this transformed principal part up here so that way we can look at it at least for the time being. So let's start with the hyperbolic case. The hyperbolic case is where the discriminant is greater than 0. So what we're going to do is we're going to choose a equals 1 and c equals 1 just to make things easier. So that's lowercase a is 1 and uppercase c is 1. So in these equations, or in these expressions here, we're going to replace this a, that a, and also all of the c's. We're going to replace all of the c's, the lowercase c's, with 1. Okay, we're going to replace all of those with 1. And if you do that, then you end up with this expression here. So I need some other colors to color coordinate here. So we have the use of C terms, those are here. So those are these ones. And then we have, so I guess maybe I could just do like, well, it might get a little bit messy if I do that. And then we have the mixed partial, that's right here. So that gives us these ones. And then we have the use of tau tau, which is right here, and that gives us these ones. So that's the principal part in, well, it's not yet simplified, but we've picked values for little a, lowercase a, and lowercase c, which have simplified the expression somewhat. So now I can scroll up here like this. Okay, so our objective is to try and simplify these expressions as much as possible. Notice that for the second partial with respect to c, this is quadratic with variable b. It's quadratic in terms of b. And the other non-mixed second order partial with respect to tau, that one's quadratic with respect to lowercase d. So what we can do is we can choose b and we can choose d so that these expressions are both 0, as long as we make certain assumption. So what we're going to do is we're just going to use the quadratic formula. So we want to ensure that this coefficient, capital A plus capital B times lowercase b plus capital C times lowercase b squared, we want to ensure that that's 0. So we use the quadratic formula on that. So it gets a little bit confusing because of the letters that we've picked. But we have b is equal to the opposite of capital B plus or minus the square root of the discriminant, divided by 2 times the thing in front of the square term, which is c. Normally when you write out a quadratic, you have ax squared plus bx plus c. But that's not what we have here. We don't even have capital AX squared plus capital BX plus capital C. We don't even have that. What we have is we have the reverse. We have capital C x squared plus capital B x plus A. So it's a little bit backwards. So that's why there's a C here in the denominator. But that's okay. Once it's clear what we're doing, that's where this stuff comes from. And so that's why we have a 2c in the denominator. But importantly, we've got a c in the denominator, so we'd better assume that capital C is not equal to 0. So for the time being, so we'll assume this, assume for the time being, assume for now, I'll say. Once we figure out what to do in this case, we'll ask what happens if capital C is actually equal to 0. So we have the same sort of thing going on over here, the coefficient for u sub tau tau. In this case, the variable, so to speak, is d. So this is quadratic in d, so we can use the quadratic formula, and we get something very similar. We get minus b plus or minus the square root of d over, again, 2c. Now we can choose b and d to be whatever we want, so long as ad minus bc is not equal to 0. So notice that these two are the same. One's got a plus minus, well, they're both the same, is what I'm trying to say. So we don't want to choose b and d to be the same. What we're going to do is we're going to choose b to be one of those and d to be the other, in the sense that we're going to choose b to be equal to the one where we use the plus, and we're going to choose d to be the one where we use the minus. So you see that we have a plus for b and we have a minus for d. We could have made the other choice if we wanted. So why are we making this choice? Why are we doing this? Well, it's going to simplify things nicely for us. So in particular, now we can say that this coefficient here is 0, as we indicate there, and this coefficient is also 0, as we indicate here. So they're both 0. So that means we're just left with this expression right there, which is all of that. So what we can do is we can now substitute in the values that we've chosen, namely b equals this expression, minus capital B plus the square root of the discriminant over 2 times capital C, and d, lowercase d, is equal to minus capital B minus the square root of the discriminant over 2 times capital C. So let's do that. Let's just color coordinate again. So maybe I'll get rid of, we don't want to use blue, I guess, because we've got a lot of blue, so let's use green. So this is this part right here, this part, and D, let's go with that one. That one's this one right here. Okay. Now what about this term right here? That's this term. That's D plus B. So if you add these two together, that's D plus B. Because you can see if you add these two together, then these two radical terms disappear, and then you just end up with minus 2b over 2c, and the 2's cancel. So that's that middle part. Now, on the right here, if you multiply that out, you get rid of the radical. That's why we wanted to choose b and d the way that we did. We chose plus for one and minus for the other, because now our numerator is the difference of squares. So we've got minus b times minus b is b squared, and then we have the square root of d times the opposite of the square root of d, which is going to give us this minus d here. So now we can simplify the principal part. Let's just write it all out. So here we're just simplifying this expression that I've underlined here. We're just simplifying it. So if you go through all of that process, give them a common denominator, things will cancel out, you'll end up with minus d over c. So this whole thing here, this coefficient, ends up being equal to minus d over c, the coefficient of the mixed partial term. So the non-mixed partials have 0 coefficients. Those are these things right here. So the non-mixed partials have both gone away. And the mixed partial, its coefficient simplifies a great deal. So it's all of that, but it simplifies and it just becomes minus d over c. So we started out with our principal part looking like this: a u sub xx plus b u sub xt plus c u sub tt. And we've done this we've transformed our variables, and we've ended up with this is our principal part. So that's our principal part now. Now we have some lower order terms here, and we also have some inhomogeneous term here, unless f was 0, and then it was homogeneous, of course. But the important thing is that our principal part is simplified by a great deal. Notice that this coefficient here is not 0 because d is the discriminant, and we assumed that d was strictly positive. So d is not 0. So that means the coefficient here is not 0. So I can divide by whatever's in front of that there, and then I end up with a principal part that's just the mixed partial derivative. And then we have some lower order terms. And if we subtract this inhomogeneous part, then that just goes into the lower order terms, and then you have a 0 here. Now, this inhomogeneous part, it doesn't go away. It's just in here somewhere. It's just in there. So this thing just gets in there somewhere. So this is called the canonical form of the hyperbolic PDE. And the coordinates are what are called the characteristic coordinates, this xi and tau. So that exhaustively describes the hyperbolic case. Well, almost exhaustively. Remember we made a little assumption? Our assumption was that c was not equal to 0. So what happens if c is actually equal to 0? Well, if c equals 0, you can repeat the same process. It's a little bit easier because you have one fewer of these capital letters to deal with. So let's suppose that capital C is equal to 0 and capital A is not equal to 0. Then you can choose lowercase b to be equal to 1. Let me just change back to blue. Then you choose lowercase b equals 1, lowercase d is equal to 1, and lowercase a is equal to minus b plus the square root of d over 2a, and lowercase c, so this is a lowercase c here, lowercase c here, because the uppercase is 0, uppercase capital C, but that's equal to 0. So with this transformation, you get it into canonical form. If capital C is equal to 0, then this transformation will do the job. Now, here we assumed that capital A was not equal to 0. So what happens if you have capital C equal to 0 and capital A equal to 0? Well, in that case, it's already in canonical form, because here's the principal part. And if capital C is equal to 0, that goes away. And if capital A is equal to 0, that part goes away. And you're just left with the mixed partial. Now b can't be equal to 0, because if b was equal to 0 as well as capital A and capital C, then you wouldn't have a second order partial derivative. You'd have a first order. So one of those has to be non-zero. So if we've assumed that A and C are both 0, then b is not 0. So what we see here is that if capital A and capital C are both 0, then you're already in canonical form. So you don't need to do anything, except maybe divide by capital B, which is non-zero. So that describes the hyperbolic case. What's next is the parabolic case, when d is equal to 0. So we won't go through the details quite as exhaustively in this case. I'll just tell you what the transformation is. So you choose a equals 1, b is equal to 0, c is equal to 1, and d is equal to minus b over 2c. Now notice that we're assuming in this case that the discriminant is equal to 0. So that means b squared minus 4ac is equal to 0. So in particular, b squared is equal to 4ac. So if c is not equal to 0, then we can divide by it. Again, that's a capital C. So if capital C is not equal to 0, then we can divide by it. In this case, the transformation that you end up with is c is equal to x and tau is equal to x minus b over 2c times t. This transforms the PDE into this form that you see here. So notice that we have only one second order derivative. It's u with respect to xi twice, and then we have some lower order terms equal to 0. So this is the canonical form for the parabolic case. Now that was under the assumption that capital C was not equal to 0. Now if capital C was equal to 0, then we know that b squared is equal to 4ac, but c is equal to 0, so that means that b is also equal to 0. So if capital C is equal to 0, then capital B is also equal to 0. And then in our principal part here, we just have that B is equal to 0 and C is equal to 0, and you just end up with the partial of u with respect to x twice. And again, a can't be equal to 0 if b and c are both 0, because then you won't have a second order partial differential equation. So again, in this case, if c is equal to 0, then you're already in canonical form and you don't need to do anything. So if c is equal to 0, then it's already canonical form, and if c is not equal to 0, then you use this transformation, or perhaps I should say this transformation right here, to get it into canonical form. Again, with the elliptic case, where the discriminant is negative, I'm not going to go through all of the details, but we'll just go through what the transformation is. So in this case, you choose a is equal to 1, and lowercase c is equal to 1, and you pick b and d just like before. So b is equal to minus capital B plus the square root of the discriminant over 2c, and lowercase d is equal to minus capital B minus the square root of the discriminant over 2 times capital C. Notice in this case, d is strictly negative. So that means these radicals, radical d, these are purely imaginary. So what that tells you is that b and d are complex conjugates of one another. Now notice we have a c in the denominator. So you might think that this means, yet again, we have to have a separate case where c is equal to 0, but it turns out in this case c can't be equal to 0, because if c is equal to 0, so if we look at our discriminant here, if c is equal to 0, then that term goes away, and then you have that b squared is negative. And b is assumed to be real, so that's not going to be possible. So in this case, we don't have to worry about a second case because it's necessarily true that c is not equal to 0. So this gives us a transformation, and it's basically the same transformation that we had in the hyperbolic case, which we have right here. Unfortunately, this is a complex transformation, but that's not a big deal because then you can introduce a further transformation. So now it's not c and tau, you can introduce a further transformation, alpha beta, and then the composition ends up being real. Notice that c and tau are in here. Notice there's also an I. So you see lots of imaginary numbers here, or complex numbers, but when you look at the composition, you end up with a real transformation. And this transformation yields u sub alpha alpha plus u sub beta beta plus some lower order terms equals 0. So this transformation isn't quite as useful, this canonical form. In the previous two cases, we managed to get rid of all of the second order terms but one. Here, we have 2 second order terms, so it's not quite as nice. However, notice that we don't have the mixed partial here, so we've sort of decoupled the variables, in this case alpha and beta. All right, so let's move to the next page, and let's look at an example. So let's use these transformations, let's use this canonical form to solve a PDE. So the PDE we're looking at is 2 times the mixed partial of u with respect to x and t plus the second partial of u with respect to t plus the first partial of u with respect to t equals 0. So in this case, we have that capital A is equal to 0, capital B is equal to 2, that's this term right there, that's capital B, and there's a 1 here, and that's C, capital C. The discriminant, b squared minus 4ac is equal to 4, so this is the hyperbolic case. So in that case, our transformation into new coordinates has has a equal to 1 and c equal to 1. This was the first case that we looked at. And then we have b is equal to minus b plus the square root of the discriminant over 2c. Now this was if capital C was not 0, but of course capital C is 1, it's not 0, so we can use that form. And if you just plug that in, you end up with lowercase b is equal to 0. On the other hand, lowercase d is equal to negative 2. Okay, so that tells us that our transformation is c is equal to ax plus bt, which is just x, and tau is cx plus dt, which is x minus t. So this is our transformation here into new coordinates. So now we can just go ahead and compute the partial derivatives, we need the partial derivative of u with respect to x and t, the mixed partial, and we also need the partial derivative of u with respect to t twice, and of course just the partial derivative of u with respect to t, but in order to get u sub tt, we're going to need to find u sub t anyway. So here's what we're going to do. We find u sub x here, and I won't go through all the details, but you can just compute them directly. And then here we have u sub xt, u sub t, u sub tt. I computed u sub xx, but we don't actually need that one. We just need these three. So again, let's just color coordinate. So uxt, that's this one here, which gives us this one. Then we have u sub t, that's this one, which is right there. And then finally we have u sub tt, which is the middle one, which is that one there. So you can just work out these derivatives and then plug them into the differential equation. And what you'll find is that you get a lot of simplification, which you expect. We know that this transformation takes us into canonical form. The canonical form for the hyperbolic case is the one where we only have a mixed partial and we don't have the non-mixed second order derivatives. And so you expect all of those to cancel, and in fact they do, and you just end up with this mixed partial here. Of course there's lower order terms. Don't forget that there are lower order terms. So what do we do to solve a differential equation like this? So this is what we want to solve right there. Well, notice that here this is 2 times capital U, the partial of u with respect to xc, plus u, and then differentiated by tau equals 0. That's this differential equation here, d by d tau. So in other words, that tells me that if I differentiate this expression with respect to tau, I get a constant. So that means that this expression right there, 2 times the partial derivative of capital U with respect to xc plus capital U, this must not depend on tau. So that means that that expression is just some constant in terms of xc. That is to say, it's constant in terms of tau, it only has xc's in it. So it's a function of xc. Because if I differentiate this thing with respect to tau, it becomes 0. So the derivative with respect to tau of this constant function, except it's constant with respect to tau, is 0. But there might be xc's in it. Because I'm differentiating, this is a partial derivative, so I treat the other variable as a constant. Okay, so what do I do now? I want to solve for this quantity. Not for that quantity. I want to solve for u. So what I'm going to do is I'm going to solve this differential equation, but notice that this is a differential equation in terms of only one variable. This is basically an ordinary differential equation now. Ordinary in terms of xc. There are no tau derivatives here that we can see. So what we can do is we can use ODE methods. We can multiply by an integrating factor. So the first thing to do is to divide by 2 to get it in the so-called standard form. And then the integrating factor here is this e to the 1/2 c. Now the 1/2 comes from this 1/2 right there, the fact that there's a 1/2 there. Because what you need is you need to multiply by something that will give you a derivative. So the thing that we want is the derivative of e to the 1/2 c, and so that's why we need, since we have a 1/2 there, we need a 1/2 in the exponent as well. Okay, anyway, so on the left, this is the product rule. Essentially, we're undoing the product rule, and so the thing that we're differentiating is e to the 1/2 c times capital U. So on the right, we have the derivative with respect to c of this e times, or e raised to the half c times capital U. So if you differentiate that with respect to c, you get this expression. So in other words, let's integrate with respect to c. So on the left, you just end up with the exponential times capital U. And on the right, you have this integral. Well, let's write this integral, which we certainly can't compute this integral because we don't know what c is. We know it's a function of c, but we don't know what c is. So let's write it in terms of a definite integral using the fundamental theorem of calculus. So this is equal to, so this expression here is the same as this expression here. However, it has some constant term in it. We know that it has a constant term because we're integrating. This is a definite integral. So the definite integral is not going to give you a constant of integration, so you need to add in the constant of integration. I called my constant of integration k because I've already been using c. I used a c up here. However, it's only constant with respect to the variable of integration. There might be the other variable in it. That's why there's a tau here. If I differentiate this thing with respect to c, then this term goes away. It's constant with respect to c. And if I differentiate this definite integral with respect to c, I end up with the thing up here, the thing that I integrated. Okay, so that tells me that e raised to the c over 2 times capital U is equal to this definite integral plus this function of tau. So now I just want to solve for capital U, which is right here. So I just divide by this term. So I'm going to divide by that term, and so I end up with an e to the negative psi over 2 there, and I end up with another one over here. So now what I've done is I've solved for capital U, and now I just need to transform it back to lowercase u, which I know that I can do. So lowercase u at x comma t is equal to uppercase U at x comma x minus 2t. Remember, that was the transformation that we made. If I scroll up, this was the transformation that we made, x comma x minus 2t. So those are right here as well. So we just make this transformation just wherever there's a xc. So wherever there's a xc, you replace that with x, and we've done that here and here. So you can see you just replace that with x and an x. And wherever there's a tau, you replace it with x minus 2t. And we've done that, and there's a tau just right there. So that's that one. Okay. And there's, of course, another xc over here, and that becomes the x. There we are. So after the transformation, we have our solution. This is lowercase u. This is the solution. Now you can see I've done a little computation here to check and make sure that this was the right answer. I wanted to make sure that it did actually satisfy the differential equation. And you should always do this whenever you solve a differential equation, especially one like this, because it's very easy to make a mistake somewhere in the middle. So you always want to check. It's just, you can call it a sanity check to make sure that you've done what you think that you've done. So you just go through and you just compute the derivatives, and you just double check that you get the right thing. And that's what I've done here.